Hello everyone. Can someone confirm if if I am audible and my screen is visible?
Yes, sir.
Okay, thanks. Let's wait for 1 or 2 more minutes and then we will start today's session. Okay, I think we can start today's session. So, good evening everyone. My name is Arpit Bal. I am a PhD scholar at Department of Electrical Engineering, IIT Bombay, and I'm also the NPTEL PMRF TA for Digital IC Design course. So I welcome everyone to the 11th live session of this course. So in the first week's live session, we did numericals related to VTH variation with VSB and drain current figuring out using the unified current equation, and numerical related to another short channel effect, that was channel length modulation. In week 2, we also consider the DIBL as another short channel effect, and also we calculated junction capacitance, and we did few more numericals related to PMOS. In week 3 session, we did numericals on trip point and few numericals on VIH and VIL. Okay, and week 4 was related to noise margin and Elmo delay. Week 5 was related to power, delay, and process variation. Week 6 was related to majorly describing a CMOS schematic. So given a function, how do we come up with the pull down as well as pull up network, and capacitance calculation and gate sizing. In week 7, we did some questions related to path delay calculation, delay optimization, logical effort, parasitic and electrical effort. Week 8, we did some questions related to mirroring circuit and pseudo NMOS logic. Week 9 was arithmetic circuits and adders. Week 10 was sign representation and multipliers. And in this week, so we will be doing some numericals related to pipelining and TD to Q, T clock to Q delay, and yeah, and other delays that are present. Okay. So without further ado, let us start with today's session. Okay. So we have a combinatorial circuit that is given to us. Okay. In the combinatorial circuit, the launch and capture D flip-flops are placed at the input and output of the circuit respectively. Okay, so this is the launch flip-flop and this is the capture flip-flop. Okay, assume that clock has a frequency of f that is equal to 1 by t, where t is the minimum amount of time one has to wait after the last input to the combinatorial circuit has changed to be guaranteed that all its output are stable. Okay? You must make the following assumptions. Logic gates have a propagation delay of d is equal to gh plus p. Okay? Where g is your logical effort, h your electrical effort, and p is the parasitic effort. The delays characterizing the flip-flops are t setup equal t hold equal t clock to q, that is equal to 0. Okay? Capture flip-flops provide zero load capacitance to the gate I5 and I6. Okay? And pipelining flip-flops are added at the output of the gate before any fan out. Fine. And they provide the same load cap to the gate as the gate saw in the unpipelined circuit. Adding one stage of pipelining will now allow you to run clock at f is equal to k by t. Find the maximum value of k. Okay, so basically we need to figure out, if we add one stage of pipelining, how much are we going to improve the clock. Okay, because f is basically f, we can say this is f pipeline. F pipeline is basically k times f unpipelined. 1 by t, we are calling it as unpipelined k. Okay, so take a moment to look at the circuit and read the question, then we will start the problem solving part. Okay, so can someone tell me, so to see what is the, to calculate the f, what do we need to do? Any idea? Does anyone remember the propagation delay part that we were doing? Okay, so we used to figure out the critical path, and based on that we used to say that, okay, so the critical path delay is x, so the frequency at which I can operate will be 1 by x. Correct? Okay, so we are going to use the same thing here as well. Okay, so but how to determine the critical path? To determine the critical path, first we need to determine the propagation delay of the paths that are available to us, right? So only after that we can determine what is the propagation delay, what is the critical path, what is the propagation delay, and from the propagation delay we can find out what is the clock frequency at which the circuit can operate. Okay, so let us start. Okay, so these gates are named as I1, I2, I3, I4, I5, I6, and I will be using the same convention, okay, while solving this question. Okay, so if anyone wants to draw this diagram for their reference, please draw it. I'll give you 1 minute time. Okay, so take a pen and paper and try to solve it with me. Okay, please draw this diagram. Once you have drawn, please let me know. Also note down the drive strength of each gates. So within the gates you can see 1x 2x being written, right? So that will be required to get the propagation delay, so please note them down as well. Okay, have you noted it down? Okay. Okay, let's wait for some more time so that others can also note it down. Okay, once you have noted it, just put it on the chat box that noted. Then we will start the solution. Because this is a good question that will brush up your previous concepts as well, and also the pipelining concept will come. Okay, is it noted? Others? Okay. Okay, we'll start then. Okay. So first thing, we need to determine what is the uh, electrical effort, logical effort, parasitic effort of each and every gate. So let me start. Okay, I1 is the gate 1. Okay, and it was 1x. Sorry, this is I2 is the gate marked as I2. Okay, and it was 1x. I3 okay, so please draw these figures with me. So we will use this to solve the numerical part. Okay, and what was the drive strength for I3? It was 2x. Okay, similarly I4. Okay, its drive strength was also 2x. Next I5. So V11, that is 4, 4, drive strength is 2x. Last is I6. Let me check what was I6. I6 is inverter. Okay. Okay. So I6 is a normal inverter whose drive strength is 1x. Okay. So please keep these diagrams handy so that when we are solving for the complete delay and critical path, that will be useful. Okay. Okay. So whatever values we have mentioned here, they are actually for gate with a drive strength of 1x. Okay, let's say for I4, so the diagram that I have drawn is for drive strength of 1x, but I have denoted that this has to be used for 2x. So accordingly we need to make the adjustment while solving the question. Okay. Okay, let's start solving the question. So let me draw a table: I1, I2, I3, I4, I5, I6, starting with C load. Okay, C load is the load capacitance seen by each of the gates. Okay, so note here, this information is going to be useful. Capture flip-flops provide zero load capacitance to the gates I5 and I6. So it means the load capacitance at the output of gate I5 and I6 is equal to 0. Is this part clear? Okay, so okay, so my I5 and I6, I can put a 0 0 here. Okay, can someone tell me what will be I1? Okay, so see where I1 is connected. So this node is connected to which gates? I3 and I4. Correct? So accordingly, from these images, can someone tell me what will be C load for I1? Okay, let us refer to this image. So I said I3 and I4 are the gates that are connected to this node, right? So I3 will offer a C load of 4 plus 1. Okay, so this is like these are connected together, right? So this will offer 4 plus 1, but the drive strength is 2. So it will be 2 times 4 plus 1. Similarly, what will be the load capacitance offered to gate I1 by I4? This is our I4. Can someone tell me what will be the load capacitance offered by I4 to the gate I1?
8C.
8C. Okay, yeah, correct. It is 2 into 2 plus 2. Correct, because this 2 refers to the drive strength and the other part is this one, 2 plus 2. Okay, so this is going to be 2 into 5 plus 8, that is 18. Similarly, for I2, what will be the value?
Same.
Yeah, I2 will also be same, because you see I2's output is also connected to I3 and I4. So it means I need to do the same thing here as well. So it will be 2 into 4 plus 1 plus 2 into 2 plus 2, that is 18. Okay, is this part clear? Okay, so what about I3 now? I3 is this gate. So what is the load capacitance that I3 sees? Okay, so this is basically 4 plus 1 into 2.
10C.
Correct. That is equal to 10. Okay, what is I4?
3C.
Yeah, because that's will it be 3C? Okay, yeah, I think I4C is inverter, right? Yeah, I4C is inverter. Yeah, correct. So it will be 3C. Okay, I'm not mentioning the C here, I'm just writing it as 3. So understand that there is a C also present here. Okay. Next, what is the gate capacitance? So gate capacitance, we can find it from here itself. Okay, so for I1 it is going to be 2 plus 2. Okay, I2 it is
4C.
going to be correct. Yeah, I2 it will be 4 plus 1. Okay, similarly we need to calculate the gate capacitance. I1 it is 1 into 2 plus 2, that is 4. I2 is 1 into 4 plus 1, that is 5. What is I3, I4, I5, I6? Can you guys start calculating this? Okay, and remember, wherever you need to multiply 2 whenever the drive strength is twice.
I3 10C. I4 8C.
Okay, yeah, I3 is correct because I3 will be 2 times 4 plus 1, that is 10C, and I4 is also correct, 2 times 2 plus 2, that is 8C. What is I5 and I6?
I5 also same with I3, not 10C.
Yeah, I5 is also 10C. I6,
3C.
yeah. Okay, now what is the parasitic capacitance? So for the parasitic capacitance, you need to see the output node of each of the gates, right? So at this point, what is the capacitance connected? Similarly, for all other gates, you need to find out. So for this gate, can someone tell me what is the parasitic capacitance? For I1? It is 2.
6C.
Correct. Yeah, it is 6C. That is 2 plus 2 plus 2. Similarly, for I2, I3, I4, I5 and I6.
I2 6C.
Correct. I2 is 6C. I3,
12C.
yeah. I4 and I5.
I5 same with
Correct. Yeah. Hello.
sir 12C I4.
Yeah, I5 is 12C. Correct. I4 is 12. Yeah. And what about I6?
3C.
Yeah. Okay. So till this part, is everyone clear, or is there any doubt? Okay. Does anyone have any doubt till this part? Okay. Then let's start calculating, starting with the electrical effort. So what is the electrical efforts formula? Does anyone remember?
C out by C in.
Correct. So basically that is CL by CG. Okay. So just you have the values of CL and CG, and you just need to divide it. So this will be 18 by 4. This will be 18 by 5. This will be 10 by 10. This will be 3 by 8. This will be 0 by 10. Okay, that's 0. This will be 0. Okay. Now what will be G, the logical effort? What is the formula?
Input gate capacitance of the gate to the input gate capacitance of the reference inverter having the same drive strength.
Correct, correct. Exactly. So that's the important point, having the same drive strength. So yeah, so can someone tell me for I1 what will it be?
4 by 3.
Yeah. I2?
5 by 3.
Yeah. I3?
Again 4 by 3.
No.
I3 5 by 3. I3 5 by 3.
Yeah, correct. So I3 is basically 10 by 3 into 2. So this factor of 2, because we need to take an inverter of the same drive strength. I3 is a gate that has a drive strength of 2. Okay, so that is 5 by 3. Correct. What is I4?
4 by 3.
Yeah, I4 is 4 by 3. I5 is
5 by 3.
yeah, and I6 is 3 by 3. That is 1. Okay. Now what is the parasitic effort? Okay, that is basically our CP by Cref inverter. Okay, so we have 6 by 3, 6 by 3, 12 by 3 into 2, 12 by 3 into 2, 12 by 3 into 2, and 3 by 3. Okay, then D is equal to GH plus P. I1, I2, I3, I4, I5, I6. Okay, so we already calculated the G, H and P. We just need to put the values here and figure out what is the D. Okay, so 18 by 4 into 4 by 3 plus 6 by 3. I2 is 18 by 5 into 5 by 3 plus 6 by 3. I3 is 10 by 10 into 10 by 6 plus 12 by 6. So please simplify these values and let me know. I4 is 3 by 8 into 8 by 6 plus 12 by 6. I5 is 0 by 10 into 10 by 6 plus 12 by 6, and I6 is 0 into 3 by 3 plus 3 by 3. Okay. Okay. So this is basically 4 cancel. This is 6. 6 plus 2 is 8. Similarly 5 cancel. This is 6 by 3, that is 2 plus, yeah, this is 6 plus 6 by 3, that is again 8. This is equal to 10 cancel. This is 12, so 10 12 22 by 6. This is equal to 8 cancel, 1 by 2, let us keep it 15 by 6. Okay, this is 2, this is 1. Okay, till this part, is everyone fine? Okay, is there any doubt or any query till this part? Okay, so now on this image itself, let me note down the d values. Okay, and you let me know what is the critical path. So I1 had a d value of 8, I2 had a d value of 8, I3 had a d value of 22 by 6, I4 had a d value of 15 by 6, I5 had a d value of 2, I6 had a d value of 1. Can someone tell me what is the critical path in this given circuit? Okay, I have noted down the delays on top of each gates. So from there, can you tell me which one?
Sir, first one.
Okay, so first one means
I1, I3, I5.
I1, I3,
Yes, yes, yes.
I5. Yeah, correct. Okay, so because that is the gate that is taking the maximum time, so that is the critical path. Okay, I have put it in dotted lines. Fine. So it means my frequency is going to be, okay, okay, let me write it here. So let me not call it directly frequency, let me call it unpipelined frequency. Okay, that is FUP. Okay, that is over the critical path delay. FUP is equal to 1 by 8 plus 22 by 6 plus 2. Okay, that will be around this 648, 48, 67, 82. Okay, that will be 6 by 82. Okay, some units. Okay, now the question is, so given this circuit, where do you think I should place a pipeline stage? What will be the ideal place to put a pipeline stage? Any rough guesses is also fine. So if you want to guess, please feel free to guess. Okay, let me give you one hint. So ideally, the pipeline stage should be placed in a way such that the point where it is placed, it is somewhere close to 50% of the critical path delay. Okay, so now tell me, where do you think the appropriate place is that is close to 50% of the critical delay? Okay, so let me write down what is the critical delay. Critical delay is equal to 8 plus 22 by 6 plus 2. Okay, so this will be 11 by 3. So let me say that this is roughly 3 something, 3.33. Okay, then this will be close to 13.33. Okay, so if it is 13.33, 50% of that will be around let's say 7. Okay, so where do you find the point where it is the delay is close to 7? Okay, so if I place it at this point, will it be fine? Because the delay is 8, that is close to 50%. Okay, so this is the path, this is the point of placing the pipelining stage. Okay, this is 3.66, sorry, 3.67, so this will also be 1.67, yeah, and it is close to 7. Okay, so this is the point where I need to place another pipeline. Okay, and after placing the pipeline, so what is the critical delay from the launch flip-flops to the pipeline flip-flops? Can someone tell me? Okay, so let me repeat the question. What is the critical delay from the launch flip-flops till the pipeline stage?
So both are having the same delay 8.
Correct.
I1.
Yeah, so both are having the same delay 8. So it means we can take 8. Okay, so 8 is the critical path delay after using one stage pipeline is 8. So FP is equal to 1 by 8. Okay, and so what is the K? K is equal to F pipeline by F unpipeline. Okay, so what is this value? Can someone calculate this?
So 1.7083.
Correct. Okay, so this is the value of my K. Okay, is everyone clear with this question? Is there any doubt? Okay. If there is any doubt, please. Yeah.
So in case if I1 and I2 both are different values, how can we select the critical path?
Yeah, so if let's say I1 and I2 are different values, then choose the critical path which gives the higher delay. Okay.
Okay, sir.
So let us assume that if it would have been 16, okay, then obviously the original critical path also might have changed. No, it would have remained same. But while placing the pipeline, so now the FP would have been 1 by 16.
So clear.
Okay. Okay. So this is the K value. Okay, that was needed. Okay. So moving on to the next question. In question 1, if you are now allowed to add 2 stages of pipelining, what is the maximum value of K compared to the unpipelined case? Okay, so here I want you to make one observation. So my k value mentions by what factor can I increase the frequency of operation, right? So if my k is greater than 1, obviously k will be greater than 1, because that is the motivation behind using a pipelining, so that my this speed increases, right? So now you can see the f pipeline is 1.7 times the f unpipelined one. Okay, so now the question asks that if we are allowed to add one more stage in addition to the existing pipeline stage that we placed here, if we add one more stage, okay, then how much k can we increase? Okay, so now tell me, where do you think you can place the second pipeline block? Okay, so you have
So
already,
in between I3 and I5.
okay, so let's say I place it here. Okay, let us assume that this is the place where I can put the second pipeline stage. Now what is the critical path from this point to this point? It's 22/6, right?
Yes, sir.
Okay, but now tell me this thing, even if I put a pipeline stage here, the first pipeline stage frequency of operation is still going to be 1/8. Correct? And 22/6 is a number that is less than 8, right? And because of this reason, so I have to still wait for the first pipeline to get completed, right? So it means my f pipeline is going to be still 1/8. Means I can't put the second pipeline stage at a frequency that is 6/22. Okay, so it means the fp remains same and f unpipelined also remains same. In unpipelined case, none of the pipeline stages will be present. Okay, and because of this reason, there will be no improvement if I put a second pipelining stage. Okay, so in this case also the k value is going to remain same, 1.7 something, right? 7083. Okay, is this part clear? Is there any doubt here?
Sir, what if we place the second pipeline and it will improve the frequency then?
Okay, let's see. If we put the second one and then it will improve the frequency. But it won't improve the frequency, right? Means because you see, so we have a bigger delay present here, 8. Okay, so it means whatever I do, I need to ensure that the data is correctly available to all the blocks, right? I can't violate that condition. So because of this, so even if I place, let's say I placed a second pipeline block, I need to wait for the data to arrive till this pipeline block end, right? And because of this, the second pipeline block's clock, I can't make it faster than the first pipeline block's clock. Correct. So it means the best that I can do is take the second pipeline and put the second pipeline's clock as equal to the first pipeline's clock. Basically, it means that the second stage is redundant. I'm not having any improvement over FP. Okay, so there was an improvement from F unpipeline to F pipeline, but there is no improvement when I put the second stage. Okay.
Okay, sir.
Okay, so moving to the next question. So we have a circuit given here. Okay, you can assume instantaneous non-overlapping clock edges and that the transmission gate opens circuits as soon as its clock deactivates. Identify the type of sequential element. Okay, can someone tell me what is it? Okay, so tell me what happens when CLK is high.
Q having D input.
Yeah. Okay, so basically whenever my CLK is high, I am getting the input reflected at the output. So because of that thing, it is a positive latch. Okay, because the moment that thing is removed, so it basically stores the previous value. Okay, so if you see, then this is an inverter, this is also an inverter. Okay, the input of this inverter I1 is connected to I2. Okay, I2's output. Okay, and the same way the input of I2 is connected to the output of I1. Okay, so basically if you ignore these two, so it basically looks like two inverters connected, like in this fashion, let's say. Okay, that resembles a latch. Correct. So this is a positive latch. Okay, so now you have to find T D Q. Okay, from D to Q, what is the delay? Okay, so for the delay to be from D to Q, it needs to pass through this point. Okay, let me call the points as A, B, C, D. Let's say this point. Then after going to this point, it will go here. So here it is connected to I1. Okay, let me call this point as B. After going through I1, so from the input of I1, it will go to output of I1. Let me call this point as C. From this point, then it will go to Q. So the path that it will follow is A, B, C, Q. Okay, so in this path, what are the gates connected? That is TG1 is connected. Okay, I1 is connected. Okay, and I3 is connected. Okay, so my TDQ will be T of TG1 plus T of I1 plus T of I3. Okay, so what is the T of TG1 given to me? 1 nanosecond. So 1 nano plus TI1. Okay, TI1 is 2 nanosecond and TI3 is 1 nanosecond. So 2 nano plus 1 nanosecond. That is equals to 2 nano plus 2 nano, that is 4 nanoseconds. Okay.
Sir, can you repeat once again?
Yeah. So in this image we are supposed to figure out what is the delay from D to Q. So now if the D has to be reflected till Q point, okay, so D to Q is the delay when the latch becomes transparent for data to go from D to Q. Okay, let us say that that's the positive latch, right? So it means the moment this clock becomes active, how much time does D take to propagate to Q? Okay, so let us say the clock is active, then D has to go through the transmission gate output that I am calling as A. Once it reaches the transmission gate output, what is the path available to it? Okay, the path to the output is like this, right? So it will go and reach point B. Point B is the input to an inverter. So this is an inverter, I1. Okay, once you reach point B, you have to go all the way to the output of I1. Okay, and the output of I1 I am calling as point C. Fine. Once it reaches point C, how will it reach point Q? It has to go through the inverter I3. Okay, so it means the path that it traverses, that is ABCQ, first through the transmission gate 1, then to the inverter I1, then to the inverter I3. Okay, and that is my T D to Q.
Clear, sir.
Okay. Okay, so the next question is to find the T setup. Okay, so for finding the T setup, so I need to ensure that the data at the neg edge, even that one is not neg edge, like the negative clock. Okay, at that point also the data is stable. So if I have to ensure that the data is stable even till the negative part, so I need to traverse the path. It means the data is available here. Okay, the path, it will go to point A. Okay, after going to point A, it will go to point B. After going to point B, it will go to point C. But I want the data to be stored within here, this point. It means that it has to cross I2 as well. Okay, so from point C, it will take the purple line and it will traverse to point D, that is the input to inverter I2. Okay, and once it traverses the path to the inverter I2, so it means at the output of inverter I2, this path will be ready the moment this latch becomes opaque. Okay, so my T setup will be equal to Tg1 plus Ti1 plus Ti2. That will be equal to Tg1 is 1, Ti1 is 2 nanosecond, I2 is 2 nanosecond. So 1 nano plus 2 nano plus 2 nano, that is 5 nanoseconds. Okay. Okay, so now the question is, so using that whatever sequential element was given to us, a D flip-flop is constructed and we need to find out what is the clock to Q delay for that D flip-flop. Okay, so the clock to Q delay will be same as the TD to Q. Okay, because in a flip-flop the data will be only reflected at the output when the clock edge arrives. Okay, so that will be equal to, sorry, T clock to Q equal to T dq of that latch. Okay, that is equal to 4 nanoseconds. Fine, that we derived just before one question. Okay, find the T hold. So in this case, as it is mentioned that you have instantaneous non-overlapping clock edges, so there is no T hold needed in this case. So T hold equals to 0. So remember why this T hold thing came up in the first place. So T hold came up so that we mention let's say the end user, that this much time you need to keep the data on hold, means stable, so as to get a reliable data. Okay, you remember that 0-0 overlap when let's say we were using a transmission gate, right? So let's say after certain time we are having the stable data available with us that can be captured. Okay, so in this case there is no overlap case, because it mentions that instantaneous non-overlapping clock edges are present, so the T hold is 0 in our case. Okay, so yeah, so these were the set of questions that I planned to cover today. And yeah, the first question is quite interesting as well as important, because it combines 2 to 3 concepts, like including the lecture that was covered in week 11 as well as lecture 7 and lecture 6. Okay, so that is quite important, so please go through it and try to do it again on your own, so that you are comfortable with the concept. And yeah, so these are the set of questions that I planned. Okay, let us revisit what we did. In the first question, we were supposed to figure out the maximum value of K. Okay, so we have a circuit that is given to us. We are asked that if we are going to add one stage of pipelining, okay, and run the clock at F is equal to K by T. So earlier the clock was running at F is equal to 1 by T, where T was the minimum amount of time one has to wait after the last input to combinatorial circuit has changed. Okay, so for this reason we need to first compute what is the critical path, to figure out what is the critical delay, and we have to figure out what is the F, that is the operating frequency, in the unpipelined case first. And for this reason what we did, we first drew some reference diagrams. So we have all the gates marked in I1, I2, I3, I4, I5, I6. Okay, and we have an information given to us that I5 and I6 gates sees load capacitance as 0. Okay, and from there, okay, that information we will use, but first we draw these reference diagrams for our convenience. Okay, from these reference diagrams we construct the table to determine the D, to figure out what is the critical delay. Okay, we find out the C load for each and every gate, and using the information I5 and I6 C load is 0. Okay, for other gates I1, I2, I3, I4, we compute the C load, we compute the C gate, that is the gate capacitance, we compute the C parasitic, okay, that is at the drain of each of the gates. Okay, then we figure out what is the electrical effort H, what is the logical effort G, and parasitic effort P. Okay, and always remember that the G and P, so we need to have the reference inverter of equal drive strength, and because of which you can see this multiplication factor 2 comes into picture in I3, I4 and I5. Okay, so having G, H and P available with us, we figure out what is the D for each of the gates. After we figure out what is the D for each of the gates, okay, I just write that down in the schematic itself for my convenience. Okay, so from the schematic we figure out that the critical path is I1, I3, I5. Okay, and the delay associated with critical path is 8 plus 22 by 6 plus 2. Okay, using that I figure out what is my unpipelined frequency, FUP. That comes out to be 6 by 82 units. Okay, now the question is, I am allowed to use a pipeline stage, one stage. Where should I place it? Okay, so the ideal placement of the pipeline should be at a position where you have 50% delay of the critical delay path. Okay, so the critical delay path is close to 13.67, 8 plus 22 by 6 plus 2. Okay, the 50% of that value is close to 7. So I need to figure out a point which is having delay close to 7. Okay, so the closest point available to me is this one. Okay, that red rectangle that I have drawn there. Okay, because at that point the critical delay from the launch flip-flops to that point is 8. That is close to 7, right? So that's why I place the pipeline stage there. And if I place the pipeline stage there, then the critical delay is 8. So my F pipeline is going to be 1 by 8. Okay, so I have F pipeline as 1 by 8. I have FUP, that is unpipelined, as 6 by 82. So K will be the ratio between that, that is 1.7083. Okay. The next question asks me, now instead of only one pipeline stage, if I am allowed to use two pipeline stages, what is the maximum value of K compared to the unpipelined case? Okay, so the answer is, if I place the second pipeline stage anywhere, let's say here, okay, still I need to wait for this pipeline stage to be over. It means my second pipeline stage won't be faster than my first one. Okay, it has to be again 1 by 8. And because of this reason, so there is no point in adding a second pipeline stage in this case. Okay, so if it would have been added, then the FP would still be 1 by 8. And because the FP is 1 by 8, FUP is same, so my K value is still going to remain the same, 1.7083. Okay, the next question was related to identifying this circuit, and this circuit is basically a positive latch. Next we had to figure out what is the TD to Q. So D to Q takes the path from A, B, C and Q, and in that path these are the gates that appear, the transmission gate, the inverter I1 and the inverter I3. Okay, so just add up the delays of those gates and it becomes 4 nanoseconds. For the T setup, we need to ensure that not only the part that is getting reflected at the output is available, but also the part that should be available, means when the latch is opaque. Okay, it means that whenever it traverses through this path, okay, this value should be available at the output, sorry, not this path, like this, okay, at the output of this gate. Okay, so it means it has to cross A, B, C and D. Okay, D and then the output of gate I2. And because of this, we need to have TG1, TI1 plus TI2, that is 5 nanoseconds. Next question was, using the D flip-flop, we constructed a D flip-flop using the element that was mentioned previously. Find the clock to Q delay. So the clock to Q delay will be equal to the D to Q, that is 4 nanoseconds. Next thing was to figure out what was the T hold for the given circuit, for the given flip-flop. So the answer is 0, because in the question it was mentioned clearly that assume instantaneous non-overlapping clock edges. Okay, and because of this the T hold is 0. Okay, so that's all we have for today, and these slides and the recorded lecture will be available on the Excel sheet that NPTEL team has shared. So I'll upload the lecture by 8:30 today. Okay, yeah, so that's all. Thanks for joining, and let me know if anyone has any query. Okay, else we can wrap up today's session.
Thank you, sir.
Yeah, thanks. Okay, thanks everyone. So let me know if anyone has any query. Yeah, sure.
Sir, negative means q equals to d bar.
No, not d bar. So see, whenever you say positive or negative, always look when this latch is going to be active. Okay, see where clock and clock bar are applied to the transmission gates input. Okay, it does not depend whether it is D or D bar. It depends when it is being reflected at the output. So look at the clock, look at when it is going to be reflected.
Okay, but sir, in this case, then when the clock is on, then the PMOS is off and the NMOS is on. So then Q traverse the path having a Q equals to D.
Yeah.
Okay, sir.
Yeah. Okay.
Thank you, sir.
Yeah, thanks.